Welcome to this video on Ernst Mach and the physics of high-speed flow. We will journey through compressible aerodynamics, shock waves, and the enduring legacy of a visionary physicist. Ernst Mach was an Austrian physicist and philosopher who made foundational contributions to acoustics, optics, and supersonic mechanics. He was the first to photographically capture the shock wave around a supersonic bullet, influencing experimental fluid mechanics and even Albert Einstein's work. The Mach number is a dimensionless parameter that characterizes the compressibility of a flow, defined as the ratio of flow velocity to the local speed of sound. This number delineates flow regimes: subsonic, transonic, supersonic, and hypersonic. When a vehicle approaches the speed of sound, the air can no longer adjust to the disturbance. Pressure waves accumulate, forming a normal shock wave. This thin, discontinuous region causes a sudden increase in pressure, temperature, and density. The sound barrier is a complex physical transition. The flow regimes shift dramatically from isentropic, incompressible subsonic flow to shock-dominated, compressible regimes, completely breaking down classical assumptions. Subsonic flow is smooth and incompressible. Transonic flow features coexisting supersonic and subsonic pockets, causing severe wave drag. Supersonic flow is dominated by oblique shock and expansion waves. Hypersonic flow involves extreme aerothermal heating and real gas effects. In subsonic flow, pressure disturbances propagate faster than the vehicle, allowing the flow to smoothly adjust. The fluid is considered incompressible below Mach 0.3, validating Bernoulli's theory. Compressibility corrections are applied as Mach approaches 0.8. The transonic regime is the most complex, characterized by local supersonic pockets that terminate in normal shock waves, dramatically increasing wave drag, known as "drag divergence." Swept wings and supercritical airfoils help mitigate shock formation in this regime. In supersonic flow, information cannot travel upstream, and the flow is governed by oblique shock waves and Prandtl-Meyer expansion fans. Thin, sharp geometries minimize wave drag, the opposite of subsonic design philosophy. At hypersonic speeds, the shock layer merges with the viscous boundary layer. Aerodynamic heating is so intense that air molecules dissociate and ionize, leading to real gas effects, mission-critical thermal protection systems, and communications blackout due to the plasma sheath. When a source exceeds the speed of sound, it outruns its own pressure disturbances. These wavefronts superimpose to form the Mach cone, the boundary of the pressure disturbance. The sonic boom is the continuous passage of this high-pressure cone. The Rankine-Hugoniot relations describe the irreversible and severe property jumps across a normal shock wave. Pressure and temperature rise sharply, density increases, and velocity drops suddenly from supersonic to subsonic, downstream of the shock. The physics of high-speed flow are not just historical curiosities. They are the governing equations behind modern applications, including the most advanced vehicles humanity has ever built. In military and civil aviation, modern computational fluid dynamics helps supersonic fighters and transports manage wave drag. Launch vehicles rely on perfectly expanded supersonic exhaust from rocket nozzles. Spacecraft re-entry faces extreme temperatures, requiring ablative thermal protection systems to cope with the detached bow shock and plasma. In summary, the Mach number is fundamental, governing all aspects of compressible flow. Each flow regime has distinct physics, and shock waves are irreversible. Ernst Mach's early work remains the cornerstone of high-speed aerodynamics.